So let's apply the stability criteria that you have seen in the last video to our case of the rigid rotor in journal bearings. As you saw in the last video, there are two ways to come to an instability when you increase, so for our case, the rotational speed. Because we know that if the rotational speed is small, very, very small, 0 for example, the system behaves stable. So there are two ways to arrive at an instability. The first one was divergence. For divergence, we have to check the sign of the first coefficient A0. Look again at the sign of the highest, of the coefficient of the highest power in lambda. It's A sub 4, and as you can see, A sub 4 is indeed always positive. It's the fourth power of omega bar. What can be said about the sign of A0? Well, it's easy because in the asymptotic case, we saw that the stiffness matrix converges to a skew-symmetric matrix. That is, the off-diagonal terms are of opposite sign. The diagonal terms are positive and tend to vanish. So this term is positive, but this term kxy times kyx will be always negative. With the negative sign, we always get something that is positive. So from this, we can exclude here divergence. Therefore, it has to be a flutter instability that we observe in the case of a rigid rotor in journal bearings. Or there is no instability? No, there is one. It's a flutter instability. And for the flutter instability, you remember, we have to check the Hurwitz criterion. So the Hurwitz minor, n minus 1. N is 4. We have a fourth order characteristic polynomial here. So n minus 1 is h3. So we have to check the Hurwitz minor for h3. So first of all, before we check the Hurwitz minor, we have to formulate the Hurwitz matrix and then look at this minor. What is the Hurwitz matrix again? For a polynomial of degree 4, so for n equal 4, it's a 4 by 4 matrix. And that 4 by 4 matrix is obtained, here you can see it, by starting with coefficient a n minus 1, so which is clearly a3, then jumping to the next odd one, so minus 2, so we have a1. Then we would jump again 2 further, so we would be at a minus 1, which of course does not exist, so we fill in zeros until we have 4 columns, because we need a 4 by 4 matrix. In the next row, we start with a sub n. We deduce 2 to arrive at a sub 2. We again deduce 2 and we arrive at a sub 0. And again, if we further deduce 2, we would have a minus 2, which makes no sense. So we add a 0 here in the last column in order to have also 4 columns here. Then we need a 4 by 4 matrix. We have filled the first 2 rows. We need another 2 rows. And for these 2 rows, we shift our result by adding zeros at the very beginning and shifting everything by 1 position, so by 1 column to the right. And that's exactly how that matrix is obtained. You can see that at the very end, 4th row, 4th column, we end with a sub 0 here in the last column. And this tells you that at that point you have to stop. Well, you could of course also count the columns and the rows to get a square matrix here, but this also tells you that you have to stop and that you did everything correct. So this would be the Hurwitz matrix formed from the coefficients of the characteristic polynomial. Now, where is the minor hn minus 1? The submatrix that we have to consider in order to form that matrix is a 3 by 3 matrix, and we start from the upper left position. So we start from the top left and count 3 columns. We count 3 rows, and here this would our 3 by 3 matrix, and we have to compute the determinant of that 3 by 3 matrix. And from that determinant, we want to solve. We set it to 0, because then we have a switch of the sign, and we want to solve that determinant of the 3 by 3 matrix for omega. We will call that omega gr, which is the German word for Grenze, or the English word would be limit. So we want to determine the limit, or dimensionless rotational speed here for this case. So in order to compute a determinant of a 3 by 3 matrix, we can apply the rule of Zarros. So we multiply all the diagonal elements, and we multiply and deduce all the product of all the off-diagonal elements. And if it happens that there are only 2 elements, then we periodically continue that 3 by 3 matrix. I will show you that in more detail. So we set that minor, the determinant of that 3 by 3 matrix, to 0 in order to get the change in sign. And from this we compute the limit, dimensionless rotational speed. And here is the determinant. Let's check it. So the product of the diagonal elements are positive. You can see that there is one product A3, A2, A1 with the positive sign, and you see it sits here just in the middle. The other one would be A1, A0, and then you take the 0 from here. So the product is 0. And the other one would be A4, A3, and you take the 0 from there. And also there the product is 0. Now you take, according to the rule of Zarros, the off-diagonal elements with a negative sign. You will have, well, if we take the true diagonal, you see that there's 0, A2 and 0, so no contribution. But as we have already used the 2 zeros here in that product, the 2 other off-diagonal products must be non-zero. And we have A1, A4 and another A1, so A4, A1 squared with a negative sign. Where is it? Here. And we have A3, A0 and A3, so A3 squared, A0 with a negative sign, and it is here. So this would be the equation from which we can determine omega bar gr in that limiting case, so the dimensionless limit speed. Well, and in order to do this, we introduce now the tilde quantity. So it's not necessary to compute A3 tilde and so on. This has to be done numerically. All these coefficients depend on the stiffness and the damping coefficients, but it is important to see the influence of omega bar. And therefore, in the last video, no, in the first video of that chapter, we derived the characteristic polynomial, the coefficients of the characteristic polynomial, and then we separated out the factors so that we showed the influence of omega bar. And now this has to be inserted here. So if you look at the situation, then you see in the first term there appears omega bar in 4th power. In the second term there will appear omega bar for A3 in 2nd power, so for one part of A2 also in 4th power, and for the other part of A2 it will appear in 2nd power only, namely coming from the 2nd power in A3. If you look at the last term, then you see that A4 appears omega bar again in 4th power. So we have in total, if we split the contribution of A2, as you can see here, into one contribution in omega bar squared and one contribution that is independent of omega bar, then we see that there are 3 terms containing omega bar in 4th power and only 1 term that contains omega bar in 2nd power. So we divide the whole thing by omega bar squared, which is now omega gr bar squared, because we set this equation to 0, and then we get the following. We get in 2nd power, well, from the first term we get A0 tilde and A3 tilde squared. From the last term we get A1 tilde squared, and from A4 we just get a 1, so A1 tilde squared. And from the middle term we get, and I changed the sign here, of everything, so multiplied by -1, we get a sub 1, a21, and a3, and the term a1, a22, and a3 tilde, everything with a tilde, is now independent of omega gr because we divided by omega gr squared already. And this equation can now be easily solved for omega gr squared. So you put that term on the right-hand side in the numerator and you divide by the term in parentheses. And this is shown on the next slide. And this will be, and then you take the square root, this will be the result for our stability limit for omega gr. At that stability limit, what happens? Well, as I said, the real part of the solution of one of these eigenvalues changes sign. And it changes sign in the sense that this eigenvalue is a complex value, so it has an imaginary part. It's a complex conjugate pair of eigenvalues then always. And exactly at the stability limit, the real part will vanish. So that eigenvalue will be purely imaginary, and you know what a purely imaginary eigenvalue tells you. There are undamped oscillations around that equilibrium. So the equilibrium becomes unstable. These perturbations, they do not decay asymptotically, but exactly at the stability limit, they are there, they will not vanish, and they lead to undamped oscillations around that equilibrium position. And this is termed oil whirl. In many cases, these oil whirls, so being close to the stability limit, can be acceptable because there are some damping mechanisms not included in the computations that are in that system. But there is another dangerous case if that frequencies of these oscillations, so as there are undamped oscillations, and we will look at that, there must be a natural frequency. If that natural frequency matches some other excitation frequency so that there is resonance. This would be called oil whip, and oil whip cannot be tolerated, of course, because it's a resonance phenomena and your shaft would hit the bearing housing. So this situation clearly has to be avoided. So for the moment, let's have a look at that stability limit. Let's compute the stability limit. Well, as a function, you could say, of the stiffness and damping coefficients, but as you know, the stiffness and damping coefficients, they depend, well, I could say either on the modified Sommerfeld number, or once you fix this modified Sommerfeld number, you get a fixed equilibrium state of the shaft within the bearing housing. So you get a fixed equilibrium position characterized by a radial displacement of the shaft, which we also call an eccentricity, and the attitude angle, a fixed attitude angle. And please keep in mind that has nothing to do, this kind of eccentricity, with the eccentricity of an imbalance. We are not talking about any imbalance here. We are still at the homogeneous solution. So the situation looks as follows. Here you can see the result for that eccentricity, and again that eccentricity is now the radial displacement, rigid body displacement of the shaft. It is not the distance between the geometric center of the shaft and the center of gravity. I'm sorry that there's twice the same letter used, this epsilon, and this leads to well, maybe to misunderstandings, but well, that's the way this problem is dealt with in the literature. No? So you can see the critical speed once represented for the modified Sommerfeld number, and on the other diagram it's represented for the eccentricity. And you can see that these plots correspond to each other because a low eccentricity corresponds to a high modified Sommerfeld number, and a high eccentricity corresponds to a low modified Sommerfeld number. You can obtain these different Sommerfeld number, modified Sommerfeld numbers, by, for example, changing the force, which means by considering rotors of different weight. so the dead load would be different. You could also, of course, influence, and this makes the thing a little bit tricky, the modified Sommerfeld number by changing the rotational speed. However, this is then a critical speed, so you change a speed and you obtain a speed. I would say that doesn't make much sense. You would change all the other parameters and fix a certain design critical speed, design speed to compute the modified Sommerfeld number and also the static equilibrium position. And from this you infer the critical speed, and then you can conclude whether your design rotational speed is lower or higher than the critical speed. What is important to remark here is that you see that in the high speed range, so to speak, so in the case where we have also the self-centering effect of that shaft in the journal bearing, there is, I would say, a kind of convergence of that function to a fixed value that is approximately 3. So you can see that for low eccentricities, so where the rigid body displacement is close to 0, where we are close to the center of the bearing housing, the critical speed, the dimensionless, of course, critical speed is around 3. Yeah? That's what can be seen from this figure, and you can see that for highly loaded rotors, so where the eccentricity becomes really large, the critical speed becomes very, very high. And if you ask yourself, but why is this the case? Think you have either a very high external force pushing your shaft to the bearing housing, so you see that the radial distance becomes here really, really large, then of course the lubrication film will create a very, very high restoring force. And this stabilizes the rotor and that instability. However, if it's like these balls where you have some water and then you see that the ball dances on the water, and this would be exactly the situation here in this range. Yeah? So if you have a very low force acting on that shaft, then I would say that shaft starts to dance in that position, because you do not fix it with a high vertical force. You do not create a very high restoring force, though there's a lot of possibility to move in horizontal direction. And this explains these undamped oscillations. So the rotor with the rather low force, so vertical force, or with the rather high rotational speed, or one could say also with a very low radial eccentricity, is rather prone to instability, while the other case, the opposite case, is a very high force. Of course, you force the shaft already in a situation that could be very critical, very close to the bearing housing, but it would be rather protected against the instability, allowing higher critical speeds then. Now let's look at the natural frequency for these undamped oscillations that occur exactly at the stability limit. So we know that exactly at the stability limit, one eigenvalue or pair of eigenvalue tends to change its sign. So the real part tends to change its sign, and the real part becomes exactly 0 at the stability limit. And we have a purely imaginary solution for that eigenvalue. Let's try to compute that purely imaginary root. So first of all, let's have a look what that tells you. Keep in mind that the roots that we are looking for, the eigenvalues, the roots of the characteristic polynomials, are dimensionless quantities. Because what we set here is we set an exponential lambda bar tau, and tau is dimensionless time. Let's insert now I omega naught, then we have I omega naught tau. Let's replace tau by the dimensional time. The dimensional time is omega times t as a replacement of tau, because we used the rotational speed omega in order to derive or to obtain a dimensionless time tau. So we have the product of omega naught, omega times t inside, and we abbreviate the coefficient omega naught times omega by nu. So what does this tell you? Omega naught is clearly dimensionless because it's just a replacement of lambda bar, and lambda bar is dimensionless. So omega naught will then be the ratio of two-dimensional quantities, namely one will be nu, because inside that, so for that argument of the exponential, you need something that is dimensionless. So t has a dimension, so nu must also have a dimension in order to create a dimensionless product nu times t. So nu is dimensional, omega is clearly also dimensional because it's the rotational speed of the rotor. So the ratio this nu one divided by omega must be dimensionless and is equal then to omega naught. So that has to be taken into account if we compute that omega naught, it's that ratio. So we see, so to speak, with omega naught, the factor, it will be the factor with which we have to multiply the rotational speed in order to get the natural frequency of these undamped vibrations, the natural dimensional frequency. I have to call that u. No? Okay. So let's plug in now that purely imaginary root in our characteristic polynomial. This is the characteristic polynomial just written with some coefficients a0 to a4, and this would be our purely imaginary root. From this equation, I can derive two equations, one for the real part and the other one for the imaginary part. As I want to solve only for this omega naught, one of the two equations sufficient. So for both equations, you should arrive at the same solution. You can check this, by the way. But here, I will just consider the imaginary part. Why? Because I'm a little bit lazy, I would say, because it's easier. It includes only two terms, a1 and a3, while for the real part you would have a0, a2, and a4. So the imaginary part of that equation is just a1 omega naught minus a3, because we have an I squared, and that changes the sign of the term, minus a3 omega naught in third power. This leads to an equation of omega 0 squared. It's just the ratio of omega 1 divided by omega 3. Omega 1 and omega 3 can now be represented by tilde quantities. A1 is independent of omega bar. For a3, as we are now at the limit, exactly at the limit, we can insert for omega bar, or we have to insert for omega bar squared gr, yeah, our limiting dimensionless rotational speed, a3 tilde. Well, and also this result can now be plotted. No? And you will find that function here, and again it's shown with respect to that radial distance, that equilibrium of the shaft, and with respect to the modified Sommerfeld number. And what you can see is for the high speed range, or I could say also for the low loaded case, where we have very high Sommerfeld numbers, where we are close to the center of the shaft, you see eccentricity is correspondingly low. So in that situation, there is again a convergence corresponding to the convergence we have seen before to that famous number 3 for omega gr. What we see here is a value of 0.5. That is the natural frequency in that range, so close to that self-centering effect, I would say, so is half the rotational speed of the rotor. And therefore this effect that is called a whirl motion is called, in this regime of course, the half frequency whirl. One should better say perhaps the half rotational speed whirl, but it's often called just a half frequency whirl. Yeah? This is a very important result to retain. So we see that there could be, just one remark, there could be resonance with that natural frequency nu. So for example, in that regime here with the half of the rotational speed. And if this is the case, then we talk about oil whip, or we call that phenomenon oil whip, and this has to be avoided. And for a large modified Sommerfeld number or small eccentricity, you saw that this frequency ratio is equal to 0.5. So you have to multiply the rotational speed of the rotor by 0.5 to arrive at the natural frequency of these undamped vibrations, theoretically undamped vibrations, yeah, because we have a purely imaginary root here. Well, that's already everything I would like to tell you, or how to apply our stability results to the rigid rotor and journal bearings. Now there is one other task left. We have to include now the imbalance. And now we come to the point where the E comes into play, where the distance between the center, geometric center of the shaft, and the center of gravity of the shaft comes into play. And this then leads to external excitation and to forced vibrations. And we have to study these forced vibrations, especially we have to know whether the amplitudes become too large, so that there is a danger that the shaft would hit or rub the house, the bearing house. Well, this will be done in the next video. And after the next video, I've seen everything for the rigid rotor and journal bearings. Thank you very much for your attention.